In today's video, we're going to be looking at Boyle's law and Charles's law. And after watching this video, you should be able to understand the relationship that exists in a gas between pressure and volume, which is basically Boyle's law, and then understand the relationship in a gas between volume and temperature, which is Charles's law. And then we're going to do a practice problem for each of the above laws just to give you a feel for how these guys work. If you're looking for a book page, it's on page 344. And this lesson will be relatively short, but it's a good stepping stone to lead into lesson 3, which is going to deal a little bit more with some more gas laws. So let's get right into it. Before we begin, I would like to mention that when dealing with these problems, you really need to change the temperature from Celsius to Kelvin. Now, not every problem is going to be in Celsius, but if you do find that to be the case, that they give you the temperature in Celsius, you'll want to change that to Kelvin. Unless they're saying like the temperature is just staying constant, then you don't need to worry about it. But keep an eye open for that, because if you have negative temperatures, the calculations get really funky. Also, just a reminder, and this was in lesson 1 Pascal is 1 Newton meter squared. Okay, so just keep that in mind. 1 Pascal is 1 Newton meter squared, and 1 atmosphere on Earth is 1.013 times 10 to the 5th pascals. All right, these two numbers may come into play in some of the homework assignments or various things that we'll do in class. So just kind of keep that in mind, that those things are there. One other thing to keep in mind is that during our study of these gas laws, we may run into things that we call an ideal gas. And actually, just about every problem, you can just assume that it's an ideal gas. And basically, if you're wondering what an ideal gas is, basically we are going to assume that the particles of the gas itself take up no space. So what I'm saying is, if I have say a 2-liter container of hydrogen, all right, clearly this container has gas in it, and we certainly account for that space, but each little pair of hydrogens, so let me see if I can draw 2 pairs, because hydrogen likes to hang out in pairs. It's a diatomic compound or molecule. Basically, we are going to assume that these 2 hydrogens take up no volume of their own, so we don't really worry about that bit to it. So an ideal gas kind of ignores that. The other piece is that the particles of the gas exert no attraction to each other. So this pair of hydrogen particles here will not be attracted to this pair over here, even though that probably isn't actually true. But in actuality, when you start throwing in all these other pieces to it, the calculations get ridiculous. And so we are going to just assume everything is what's called an ideal gas. Okay, so don't get confused about that. It's just making it actually easier, that we don't have to worry about these other things going on. So let's get right into Boyle's law, and then we'll go into Charles's law. Robert Boyle, he was a chemist and a physicist during the 17th century, and basically Boyle noticed that in a fixed sample of gas, and if the temperature stayed constant, the volume of the gas would vary inversely with pressure. Now that sounds kind of complex, but basically what he's saying is, if the pressure of a gas decreases and you aren't changing the amount of gas in that container, the volume will actually must increase. The volume of the container must increase. And so sometimes I think a picture is worth 1,000 words. If you have, say, a container here, and it's got all these gas particles in it, and so I'll draw these here. Let's say I decide to make this container about half as big. Okay, so let's say transfer those gas molecules into this container. It's about half as big. These gas molecules are going to be much more squished, much more compacted together, and they're going to be bouncing off one another, and basically that's going to cause the pressure to increase. But what happened to the volume? Well, the volume went down. So that's an inverse relationship. Basically, pressure increased, volume decreased. Now, on the flip side of that, and I don't have the space to draw it in here, but let's say I increase the size of this box to be about double the size. Now, I don't know if this is double, but we'll say about double the size. In this box, I still put the gas molecules, but there's just as many in there, but there's a lot more space. It's a lot more roomy. And so the volume has increased, absolutely, but what has the pressure done? The pressure has decreased. And again, that's an inverse relationship. That's basically all Boyle's law is saying, is that if you keep temperature constant, you don't add any more gas to the system, the pressure will increase if the volume decreases, or if the volume increases, the pressure decreases. So that's basically all Boyle's law is. And if there's a little nifty equation that can be written down where basically P1 times V1, which is pressure, times the volume, equals the new pressure times the new volume. All right, and basically that's it. Right? So that's Boyle's law in a nutshell. So if you're kind of confused, let's do an example problem of what I might expect you to be able to do. All right, so just quickly let me change my pen color here so that you can actually see it. Let's see here. Red sounds, all right, green, sure. How does green look? Good. All right, so it says a 3.5 liter of hydrogen gas exerts a pressure of 2 times 10 to the 5th pascals at 295 Kelvin. All right. If the temperature remains the same and the gas is allowed to expand to 7 liters, what pressure will the hydrogen exert? So without even calculating anything here, what is happening? Well, basically I start with a container that is 3.5 liters and it's expanding to 7 liters. So if the volume is going up, what is going to happen to pressure? Well, it's an inverse relationship. Pressure is going to go down. So by golly, I better see a number smaller than this or my calculations are probably wrong. Okay, so just keep that in mind. Like, you don't always have to immediately jump to an equation. You can kind of use some intuition in terms of what is you think will happen based on the calculations. Now, we are going to actually find out what the pressure is, and basically I'm going to use Boyle's law, which is P1 times V1 equals P2 times V2. And my P1 is 2 times 10 to the 5th pascals, and my V1 is 3.50 liters. And then on the other side of this bad boy, we have a V2 of 7 liters and a P2 of, well, we don't know. We'll call that X. Right, so basically I'm just going to throw this in an equation here, or into the equation, times 10 to the 5th, that's 2.0, times 10 to the 5th, times 3.50 liters equals X times 7 liters. What is X? Well, if you just do some algebra and divide both sides by 7 and do this multiplication, I get X to be 1.00 times 10 to the 5th pascals, because we're looking for pressure. And that would be the answer. Okay? So it's basically using Boyle's law to figure out what the pressure was. Now, I could have done it differently and asked for the volume. It wouldn't really matter. You still would use the same equation and still do the same stuff. So hopefully that wasn't too bad. All right, let's move on to the next thing. The next one's dealing with is Charles's law, and I believe how you pronounce his name is Jacques. He was a French scientist. Jacques Charles, if I'm pronouncing it incorrectly, I apologize. Did an experiment that discovered if you reduce the temperature of a gas, the volume decreases. All right, and this is kind of making sense because we had talked about in chapter 13 about the tire pressure on your car and how that tire pressure gets lower in the winter because it's so cold outside. Okay? On the other side of the coin, if you will, on the flip side, if you increase the temperature, the volume will actually increase. Okay, so it's kind of similar to Boyle's law. Instead of using pressure, though, this time it's using temperature. All right? And this is the handy-dandy equation for Charles' law. And this is where I made a note of this at the beginning of this video, but anytime you use Charles's law, you'll definitely want to convert those temperatures to Kelvin. You got to do it, or else you can get some really funky answers, because you can get negatives for temperatures, because there is no negative in Kelvin, but there certainly is in Celsius. So let's take a look at an example here on Charles's law and what I might expect you guys to do in class. It says a sample of neon gas occupies 2 liters at 22, this should really say degrees Celsius, I apologize, a little degree sign there. How much space would the sample occupy at 68 degrees Celsius, assuming the pressure remains constant? Okay, so first thing we do is we have Charles's law here, which is V1 over T1 equals V2 over T2. All right, and so basically I'm just going to write down my knowns. My V1 is 2 liters. My T1 is 22 degrees Celsius. And right there, a little flag should go off in my head. That is in Celsius. I want that to be in Kelvin. And so to make it Kelvin, we're just going to add 273.15. And if my math is right, that would be 295.15 Kelvin. Okay, so that's my new T1, is that temperature right there, 295.15 Kelvin. I'll just make my little divider here. My V2, I don't know, so I'm going to call that X. That's what I'm trying to find out. And my T2 is 68 degrees Celsius. Now again, a flag should go off in my head. I want to make this be in Kelvin. So I'm going to add 273.15 to it. And that is 341.15 Kelvin. Okay, so basically I'm just going to throw these numbers into this equation. And so I have 2.0 divided by 295.15 equals X over 341.15. And these are Ks, this is liters. And basically, if you just do the math here and cross multiply, X will get you 2.3 liters. And that would be the answer. Okay, so hopefully you have a better understanding of Boyle's law and Charles' law, and you'll be ready to go for the next video, and we'll see you then.